Hello everybody. Let's talk about another example related with the arc length. Okay, the arc length. So as another reminder, the arc length formula, which is the integral from a to b, square root of 1 plus the derivative of the given function, square d of x. Okay. And occasionally the problem gives to you its write x in terms of y and ask you from y, let's see, equals 1 to y equals 4, something like that. If that's the case, what you can do here is you can write the alternative formula, which is dx dy. Take the derivative with respect to y, and then for here is dy, okay? So, but the idea is exactly the same thing. Let's look at one example here. So, example 1. So given y equals, let's see, 3 over 4, x to the power of 4 over 3, minus 3 over 8, x to the power of 2 over 3. Okay, and then plus 6. And then find the arc length of the curve y from x equals 1 to x equals 8. Okay, so that's the problem we're going to deal with. So you can see that immediately we can set our interval, which is from 1 to 8, square root of 1 plus dy dx, right, squared, and then dx. Okay, so that's something we can directly tell. And you know, y is given to here, so the dy dx, as you can see that it says pretty easy to evaluate. This is going to be x to the power of 1 over 3, and then this is going to be negative 1 over 4, x to the power of negative 1 over 3. Okay, it's just based on the power rule. It's nothing special here. And now, you know, I got this, and I started to evaluate 1 plus dy dx squared, which is 1 plus x 1/3 minus quarter x to the power of negative third squared. Okay, that's something we know. Now I'm gonna expand this, which is 1 plus x to the power of 2/3 minus 2 times x to the power of third times 1 over 4 times x to the power of negative third. Okay, and then plus, actually it's 1 over 16 x to the power of negative 2/3. Okay, you can see I keep this parenthesis. And, you know, this is exactly the expansion from this square. And let's still keep that, you know, x 2/3. It turns out, you know, if you evaluate this, x 1/3 times x to the power of negative 1/3, it becomes into x to the power of 0, which is 1. 2 times a quarter, which is half. And I have minus here, so it's minus half. And then plus 1 over 16 x to the power negative 3, negative 2/3. Okay. Now you can see that if I make the operation of those two constant, and it will give us is x to the power of 3/3, 2/3, plus 1 over 2, and then plus 1 over 16 x to the power of negative 3 over 2. So why I want to show you this? Because if you make a comparison with this part and this part, you can see the only difference is the sign of the middle term, which becomes from negative to positive, okay? But also, this is exactly the expansion from this square. So that should give us some idea is it possible I can rewrite this in a perfect square form? And the answer is yes. So what we can do is, if we alternate this negative into a positive, in other words, change the minus into plus, we're going to have this x third plus 1 over 4th x to the power of negative third squared. And you can verify this is exactly if you expand this, it's going to give you exactly this, okay? Now, a couple of things I want to address a little bit for this. First of all, why we want to rewrite our result and put it into a perfect square form? Because, this 1 plus dy dx in square here, keep in mind, when we evaluate that integral, it's still inside of that square root. So if we can write into a perfect square, then square root and square, it actually cancel out. Okay, so that's actually a big advantage, okay, for solving the arclengths. Okay, and then the other thing is, how do I identify this? Then two simple formula here, which is if you have a plus b squared, you're going to have a squared plus 2 times a times b plus b squared. While if you have a minus b squared, you're going to have it a squared minus 2 times a times b squared. Okay, so you can see that only in the inside part, the middle term, the sign is changing, and then when you convert it back into the perfect square, all you need to do is to alternate the sign. Okay, so that's where this raising from. Okay, so that's the perfect square formula. Okay, so with this, things become easy. What we can do here, we can follow this. So I can starting to evaluate this integral. It's going to be from 1 to 8, right? Square root of x third plus a quarter x to the power of negative third squared dx. Okay. And like I said, you'll see square root and square root cross out, so it's from 1 to 8, x third plus a quarter x to the power of negative third dx. Okay. And it turns out this integral it's very easy to evaluate it, which is x third plus 1 over x plus 1, and then 1 over 4. This is x to the power of 2/3, which is negative third plus 1, and then over 2/3. Okay. Evaluated from 1 to 8. Okay. To 8. And so you can do some simplification. 3x to the power of 4/3, and then for this part, it's going to be 3x to the power of 2/3 over 8. Okay, and then from 1 to 8. Okay, so you can put back to when we plug in, guys. I'd rather to let you to replace this 8 into 2 cube. Why? Because if you place 2 cube, there are a lot of cancellation. So let's do that. So 3 times 2 cube to the power of 4/3 over 4, plus 3 times 2 cube to the power of 2/3 over 8. Okay, and then minus. We plug 1 in, which is 3 over 4 plus 3 over 8, because 1 raised to n power it's 1. Okay, so this part you can cancel out, so it's 3 times 2 to the power of 4th over 4, plus 3 times 2 squared over 8. Okay. Minus, for this part you can rewrite into 6 over 8, so it turns out it's 9 over 8. Okay, this part. And then, so basically it's calculation, okay, simple calculus. So it's just 3 times 2 to the power of 4th is 16 over 4, plus 3 times 4 over 8, minus 8 over 9. Turns out what we have here is this is 4, so it's 12, okay, plus 12 over 8 minus, this is 9 over 8, okay, 9 over 8. So it turns out we have is 12 plus 3 over 8, so it's give us, okay, so we're done. Alright, so I think the key for this problem as a reminder is how do we, take the derivative and then calculate this 1 plus dy dx squared and then rewrite into a perfect square form and then plot back to the integral. Square root and square root cancel out, and then starting from here to the very end, it's a simple, definite integral problem. Okay, so I hope you enjoyed this. Thanks.